We're continuing with optimization problems. This is an example. Find the largest area that can be inscribed in the ellipse x squared plus y squared divided by 16 equal to 1. This is the ellipse, and we're inscribing a rectangle in here. So the first thing to notice is the constraint. Constraint is the equation of the ellipse. The next thing is to figure out the objective function. Objective function is the area of the, as it says, find the largest area. So we're trying to maximize the area. And we're trying to find the maximum area. And so the area is related to this length and this length. This length and this length. Now, looking at this, and since the ellipse is centered at the origin, the ellipse is very symmetric about the x and y axis, and therefore I can actually say that it's the rectangle inscribed in it is going to be very symmetric about x and y axis, and I will have basically 4 pieces in here to worry about, and each piece is congruent. One here, another one here, another one in here. So it suffices to actually figure out the area for those pieces rather than the entire rectangle. And so those are this length times this length is going to give me the area for that one piece, and I multiply it by 4 and I get the area function. How do I find that? This one is the x value for the vertex that sits on the ellipse, and this other one is the y value for the same vertex. So the objective function is area equal to x times y. Now we want to use the constraint to make this a function of one of the variables. How do we do that? We have to solve for y in the constraint. So solving for y by subtracting x squared, then multiplying by 16. Now, this is y, that's y squared. It should give me two solutions, but I'm going to ignore the negative one. I'm just going to go with the positive one because I'm assuming that the point is in the first quadrant, and then I'm ignoring the other points in here. So this is the area function. Oh, and I should have put a 4 in here because it's 4 times that x. The entire area is 4 times x times y. Now I replace this in here, and I get either I can keep the 16 inside or outside the square root, and basically, or I can write 16 coming outside becomes 4. 4 times 4 is x. And this becomes my objective function. Before moving on to the derivative, and I want to mention something about the objective function that makes it undesirable to take the derivative of it directly, is the domain. Let's see what the domain is. So to find the domain, I'm assuming x can start from 0 and it can end at that point. Where is that point? That point is where the ellipse intersects the x-axis in the positive side of the x-axis. So it's where y is equal to 0. And here, if I set y equal to 0, I get x squared equal to 1. X would be plus minus 1, and that one is the 1, not minus 1. This one is the minus 1. And so the domain is 0 and 1. Next thing is to take the derivative. As soon as I start taking derivative, and I worry about finding critical numbers as well, as soon as I start taking derivative, having a square root starts to bother me. So, but then I remember a little fact from the past that if the area is maximized, then the area to power 2 should be a maximum area to power 2, and the other way around. So if I maximize the area function, it's the same thing as if I maximize the area function to power 2. So instead of taking derivative of a of x, or instead of having a of x as the objective function, I switch to a of x to power 2, and I call it g of x. And so g of x is the entire area to power 2. So it's 16 squared times x squared times 1 minus x squared. Rewriting it is 16 squared times x squared minus x to the power 4. Now, new objective function, because maximizing this one is the same thing as maximizing a of x. Now, take the derivative of the new objective function, derivative, and we end up, this is 16 squared, and it's a coefficient, it stays, and inside I will have 2x minus 4x to the power 3. Now, the next step is to find all the critical numbers. So so you may have extra critical numbers because you found g of x, but it doesn't matter. I have to do my testing to make sure that I'm arriving at the maximum area to power 2 anyway. So that's that's one way of doing this, finding the critical values for the area to power 2 function. And so now, finding the critical points. Set this one equal to 0. And it gives me 2x minus 4x to power 3 equal to 0. This solves, and we factor 2 and x. And we arrive at x equal to 0, or x is equal to plus or minus square root of 1/2. The next thing to do is to test your critical numbers and a few other things that we will mention in there. First, I'm going to erase the board, and then we come back to it. Now we found for the new function, for the new objective function, we found 3 different critical numbers. One of them can be eliminated right away because it's not within the domain of the area function. So negative square root of 1/2 can be eliminated right away. The other two, I can now use closed interval method to find what if any of them creates the maximum area. Looking at the, now I can use either of them. But I'd rather use the one that I'm actually calculating for. And so what I do is use the test closed interval. And I figure 2 endpoints of the closed interval, which incidentally is one of the critical numbers for the new function is in there, and the critical number. Plugging in 0 in the objective function, the original objective function, will render a 0. Plugging in 1 will give you a 0 as well. Plugging in 1/2, square root of 1/2 gives 1 minus square root of 1/2, which is square root of 1/2 again, times square root of 1/2, and that would be 16 divided by 2, which is 8. Now, endpoints, critical numbers, and the maximum is 8 by closed interval method, because the function is continuous on the closed interval. This is the maximum area. And it was attained at x equal to square root of 1/2, or square root of 2 over 2.